recording was stopped. Okay.
Yeah, not sure why, Josh, but glad we got it back up.
Okay, I just didn't want to continue on until that was taken care of. So, okay. So, the primary objective of section 3 is to understand where resource concerns, such as nutrient loss via runoff and tile drainage, may be in the watershed. The first tool in this data set is by field slope statistics. So you provide the field boundary and the DEM, and this tool generates a slope table and raster in percent rise. It then uses the input field boundary feature class to generate those slope statistics by field, which are outputted to the table. So this is what the output looks like from that tool. On the top there, you have the slope table, the field boundary. Each field boundary is given an ID throughout this process. Then you have, it gives it the mean slope, the slope of the 75%, the percent of the field that's less than 1% slope, and then all the way up to greater than 15% slope. The raster that's created, as you can see below, once it's symbolized, in this case here, the higher the slope is symbolized up in red. So those are the areas where your landscape is sloping the steepest. Also, you can symbolize via the mean slope of the field. Since you have that field boundary, you can join that up with since that table has the field boundary ID, you can join that to your field boundary data set, and you can visualize the mean slope across all the fields so that you can see which fields are going to be sloping the most. The next tool set, or the next tool, is tile drainage classification. Once again, since this is a field characterization section, you will provide the field boundary feature class. You would be providing the soil. And a lot of times these tools will go ahead and pre-populate these out of the same geodatabase. So you provide the soil and the slope. And then whoever is running the tools, once again, be it you or another GIS technician, would determine the condition that is used for this to try to figure out if there's tile drainage there or not. For sure, there's one condition that is needed, which is greater than or equal to 90% of the field is less than 5% slope. And then you can be as restrictive or inclusive as you would like. So you would choose and or. If you use and, the field has to meet both, or is one or the other. Then the soil characteristics that you are using for the tile drainage classification there's actually 3 options that you can use. The first option is mean hydric soil percentage is greater than or equal to 10%. The second is if greater than or equal to 40% of the field consists of poorly defined soils or poorly drained soils. Those would be any soil that is D class of some sort. And then the other option, which was just recently added to the tool set, is more than 40% of the field has a shallow water table depth, which is less than 50 centimeters in the months of April, May, and June. Now, this isn't saying for sure that the field is in fact tile drained. We don't have that ability to determine, if there's tiles underneath the field from elevation data sets. This just kind of is suggesting those fields that may be drained given the conditions where tile drainage or tiles are usually located. So once again, this creates a table that can be joined to the field boundary data set. It shows the percent of dual drainage, percent slope, and it provides the whether it is drained, whether it's not drained, or if the field itself is not an ag field. The field boundary data set is got a column in there that says whether the field is ag or not based off of the crop history and land use. The next tool then, as we continue on through, is D8 distance to stream. D8 is just kind of the process that's used with the flow accumulation and flow direction. And so this distance to stream calculates the horizontal distance to the channel from each grid cell as it moves downslope according to the flow model. And this is one of those where you could choose whether you want to have your stream reach be with or without water bodies. As you can see in the image underneath the tool inputs, this actually has the stream or has the water bodies included within it, because you can actually see the ponds that are don't have the distance to stream within it. If this was going with just the stream reach without the water bodies, you would see values within there. This tool is going to be, or the results of this tool are actually going to be used in the next tool, which is probably one that is going to be useful for a lot of the users. And that is runoff risk assessment. This tool is based on the Minnesota Phosphorus Index. It takes a look at the slope and how far, or takes a look at the slope and how steep it is to how close it is to the stream. It also prioritizes the fields where multiple erosion control practices are most needed. As I stated before, the fields are given a value of whether it's ag or not. This is only going to look at those ag fields. And it doesn't necessarily utilize the close to stream as in just a distance. It's used as a proxy for, or sediment delivery ratio is used as a proxy for the stream proximity. It takes a look at how far the field is from a particular stream and gives it the sediment delivery ratio. The output then is, or the fields are given a value of A, B, C, or D, depending on how much of a risk it is for runoff. And essentially, the user is given two options for each of the input variables. You can provide third, slope values that are okay, so sorry. The user can provide thresholds for classification of slope and the sediment delivery ratios into high, medium, or low classification. So you would give those values that are the breakpoints for high and medium as shown in the red box. Or if you just were to run this without any putting in any values, those thresholds will be automatically generated using a 20-40-40 split. If you want more information on how those are calculated, you can go take a look at the manual. It actually takes a couple different, it has a couple pages on how these are determined. So as I stated, the runoff risk is given a value A to D, A being a very high runoff risk. If we look back at the little chart, that's going to be areas that are close to a stream and that are very steep, which would make sense. And so your table shows that the last column in the table there has runoff risk. So high, very high, high, moderate, and low. It also provides how the sediment delivery ratio is considered low, medium, high, also with the slope. It also shows what the slope value in percent rise is within each field, the actual SDR that's used for those fields. And so since just like all these other tables that are produced within the ACPF toolbox, you can join the table back to the field boundary data set. And as you can see in the image there on the right, you can show which fields are critical for runoff risk and which ones are very high, so that you can focus your efforts towards those fields with trying to reduce runoff. And with that, we're to steps 4 through 6, which is where Emily is going to take over.
Okay, Joshua, if you could maybe stop. Yeah, perfect. Yeah. And I'll share my screen.
There.
Perfect. Okay. All right. So can everyone see that okay? Josh, does that look okay on your end?
Yes.
Okay, perfect. All right. So I'm going to talk about steps 4 through 6. So Josh has outlined the really critical preparation work that goes into the steps that I'm going to talk about, which are identifying those key areas in the landscape where we have opportunities to cite conservation practices. I think, steps 1 through 3 can seem kind of nebulous or tedious, and you really want to get to identifying those opportunities, right? But those first 3 steps are really critical in ensuring that steps 4 through 6 are really citing practices or finding opportunities in the right places. So I'm going to start by talking about step 4, which is precision conservation practice citing. There are 7 steps in that tool: depression identification and drainage area, drainage water management, more terrain derivatives, and then we look at grass waterways, contour buffer strips, and edge of field bioreactors. So we're going to start with talking a little bit more about depressions. We talked a little bit about this in steps 1 through 3. We're going to revisit it here as we start to think about identifying opportunities for practices. So the first process here is to identify areas that are true depressions. So many locations, particularly in the Midwest where we've seen glaciation, are going to have areas of depression. Those areas are often spots where we might have blind inlets or where there might be some subsurface drainage happening. They're often places where we might have potential best management practice opportunities. So for example, putting in some grass filters around those drainage inlets, or even doing wetland restoration in areas where that might be suitable. So identifying those true depressions are important steps. So in this first step, what happens is we identify locations where there are depressions, and then we identify those polygons, those polygon areas. So you can see from the tool on the right-hand side of the slide that our key inputs here are the unfilled DEM, as well as our soils raster and our field boundary feature class. It's also important to put in our stream reach center lines and our water body polygons as well. So those inputs are important. So the tool, when we identify those polygons, we're looking for hydric soils. We're only considering agricultural fields. And then we don't want to identify depressions that are going to intersect with our stream or are centered on our water bodies. There are 3 key criteria that users can adjust. Those are in that red box in the tool. So that would be the minimum percent hydric, the minimum depth of the depression in centimeters, and then the minimum surface area. These are important when we start to think about the potential best management practices that we might place in these depressional areas. Some of those practices, particularly related to wetlands, will have criteria set forth in conservation programming that we want to be mindful of when we set our minimum threshold values. And then our output includes that depression feature class, and then there's an option to include a raster that will show depth variability in these different depressions. So when we look at what the outputs might look like in the depression identification step, you can see the table on the left-hand side of the slide. So each one of the depressions that we identify are going to have a different identification number that's unique to them. You'll also see the percent hydric that each one of those depressions has. And then you'll also see the maximum depth in centimeters. These percent hydric and maximum depths, remember that those are going to be reflective of those minimum thresholds that you set when the tool was running. You can see the polygon output from this step, so identifying those depressions, as well as the raster output. And again, that raster can be really useful because it can demonstrate depressions where the depth is greater, so this depression here in the center, versus areas where we might have a shallower depression. So for example, out in the northwest corner of this image. I talked a little bit 2 slides ago about why it's important to consider some of those minimum and maximum values, or minimum values for percent hydric, depth, and surface area. These are 2 examples from Minnesota. So for example, for the Conservation Reserve Enhancement Program, some of the key requirements include a minimum percent hydric soil of 60%, a minimum depth of 30 centimeters, and a minimum surface area of 8 acres. So if you're trying to identify depressions that might be compatible with Minnesota's CREP program, it might be important to consider some of those thresholds as what you would use in the tool. I've also included Iowa's program criteria here, but just considerations as you look for those depressions in the landscape. The next step is to identify depression drainage areas. So this tool is pretty straightforward. It's just going to delineate the drainage area to each one of those unique depressions that were just created in the previous step. So the only inputs to this step are the depression layer and then that unfilled DEM. And the output are the catchments that are associated with each one of those small depressions. You can see the output table and the output shapefile that would be, or the data layer that would be associated with that. So for each one of the depression IDs, there's a drainage area in hectares that is provided. In the map or the image on the lower part of the screen, you can see each one of those depressions, that's raster. And then you can see the depression catchments or the drainage areas around those polygons, which is denoted in that lighter teal or blue color. All right, so the next step is actually citing a conservation practice. So this is drainage water management. So drainage water management is useful on fields with relatively flat topography. So if this isn't a practice that's familiar in your landscape, there are some images on the lower part of this slide that shows the general principle of drainage water management. So drainage water management means that in certain parts of fields or in whole fields, we'd install gate structures, which you can see a photo of in the lower part of the slide, that basically raise and lower the water table in a particular agricultural field. So after harvest, when we're not wanting to be in the field, we might increase that water table, increasing the opportunity for denitrification to occur in those anaerobic environments in the soil profile. However, before planting or during harvest, we might want to lower that water table, right? So we can get into the field. So drainage water management allows us to regulate the water table. Because the practice works best in fields with relatively flat topography, this tool is identifying opportunities within our tile drained fields where the contour zones vary relatively little. So anywhere from 0.3 to 1.5 meters. This is important because for every 0.5 meters approximately of change, we would need an additional gate structure. This practice, I want to say, can be relatively expensive to design and install in areas with slopes that are steeper than 1%, again, because of those increases in control structures. So to run this tool, you need your field boundary class. So we're looking at the field scale, an unfilled DEM, that drainage table that Josh talked about in steps 1 through 3. And then the user has some discretion about the contour interval that they want to consider. So again, somewhere between 0.3 and 1.5 meters. The more you move toward that 1.5 meter, the greater the likelihood that you may need more gate or control structures. And then the user can also decide whether they would like to consider the minimum percent of the field that defined contour must occupy, or the minimum acreage. And then the output is drainage water management contours, which are going to show basically zones of a field where this practice might be suitable. One caveat I want to mention here is that actual implementation of this kind of practice would require a much more detailed survey of a field, because we know that field topography and drainage patterns are going to vary and may be very different than what the ACPF products might provide. Tile drainage patterns need to be surveyed. You need to think about potential impacts of ponding on our on-fields and in neighbors' fields from changing tile drain patterns. So again, this would be one where we'd want a much more detailed evaluation of the landscape if we were going to go out and actually cite this practice. The tool is really just identifying opportunities. So this is what the output looks like. So you can see in this image on the right side of the slide, those polygons where we've identified that contour interval. So you can see those in each field. So for example, this field here, there's just one suitable contour interval that would be suitable for a drainage water management structure. When we look at the table, you can see that each one of the fields is delineated here. The acres, for example, that would be suitable for drainage water management, the total acres in the field, and then the percent of that field that would be a candidate for drainage water, a contour zone for drainage water management. Similar to when we talk about depressions, it's important to think about the settings that the user can derive in the context of what the goal is for that conservation practice, that drainage water management practice. So here you can see 3 different scenarios where someone might be considering drainage water management. And each one of these scenarios is going to change those user-defined settings slightly. So in this case, each one of these is going to have the same contour interval, 0.3 to 0.6 meters, again, really sticking closely to that 0.5 meter contour interval range. But then the defined settings for percent or acres may change not only which one might be most appropriate, but also the values depending on what the goal of this practice is for the landowner or stakeholder. So if we're looking for suitability for approximately 1/3 of the field, you can see that that's a percentage, and that's indicated in that minimum percent of field. If we're looking at economic suitability, perhaps an acre threshold within a field is more appropriate, so 20 acres, for example. And if we're really looking for a restrictive set of criteria for suitability of drainage control systems, perhaps the minimum percent of field would be closer to 60. So really try to think clearly about the purpose as you set forth some of those percentages. The next tool I'm going to talk about a little bit is precision conservation practice siting for more terrain derivatives. So more terrain derivatives include the stream power index and the topographic wetness index. That stream power index, or SPI, is basically just a measure of the erosive power of flowing water, which is based on the assumption that discharge would be proportional to our catchment areas. The critical part here is that a high SPI indicates high erosion potential. And these areas where our stream power index may be higher, may be spots where we consider using conservation practices like grassed waterways, for example, which we'll talk about next. The second more terrain derivative that we look at is the topographic wetness index. That's going to allow us to identify areas where our soil properties would predict zones of saturation. And so higher topographic wetness indices would indicate greater saturation. So if we look at an output from more terrain derivatives, what you can see with that stream power index are those areas in red are going to be areas where we'd expect high erosion potential, and areas where we might expect saturation to be occurring as well. If we look at topographic wetness, we can see areas of the field where we'd expect wetness to occur and have some saturation occurring, as well as those areas where water is consistently flowing. So SPI is particularly important for siting grassed waterways. To do that, the user is going to define some standard deviation around a mean SPI value or a specific SPI value that identifies areas where grassed waterways might be most suitable. So you can see that for this particular tool, you're going to put in your field boundaries and then that stream power index raster, which was created in the previous step. And then again, you can either select a standard deviation threshold or a value threshold for that SPI or that stream power index. SPIs above the selected threshold will be connected together. So those individual raster cells will be connected into a polyline. They're thin to the width of one cell. And then the output is a polyline layer of grassed waterways. Those outputs or those polylines are clipped to fields. We're only looking at our crop fields here. And then any polyline that's less than 50 meters in length would be excluded from the output. So your output would look like this. So you can see that those highlighted polylines in this particular image, those would be areas where we would expect, where we might identify opportunities for grassed waterways. You can see in that red box in the lower right-hand side of this image that there is clearly a grassed waterway that's already been installed, yet the polylines for that grassed waterway are not connected. So field verification is a really necessary step in identifying opportunities for grassed waterways. The next practice that you can cite or identify opportunities for in the ACPF are contour buffer strips. So contour buffer strips, remember that they're strips of grass or forbs that you can place at different locations up the shoulder back slope and then down into that foot slope to slow water down and hopefully also slow down sediment and phosphorus. So for ACPF, there's a mask of between 4 and 15% slope, which is generated for agricultural fields. So that means that what we're looking for there are areas in those fields between 4 and 15% slope. And then we generate contours within those slope areas on a by field basis. So our contour intervals are chosen so that the resulting contour buffer strips are spaced approximately equal to our NRCS recommended spacings using the third quartile slope. And you can see that depicted in that image in the lower right-hand side of the slide, where the slope length and the steepness vary depending on the situation, and the spacing changes as well. So when our slope length is longer and our slope is smaller, the spacing might be closer to 250 feet. But as that slope length decreases and our slope becomes steeper, the spacing may be closer to 150 feet. So basically this tool is kind of getting at that principle. So you can see the input requirements here, as well as our output data layer for contour buffer strips. So again, when we think about defining these contour buffer strips, This tool is based on terrace spacing and then contour spacing. So we're really thinking about the percent rise as well as that slope length to understand the spacing needed for these contour strips. So here are some examples of that shown in with these green lines in the image on the right. Those are contour buffer strips that have been placed in the landscape. The last step of precision conservation practice siting is edge of field bioreactors. Bioreactors are only available to be installed in tile drained agricultural fields. So we exclude fields that are likely not tile drained or not agricultural. Our potential sites for these bioreactors are filtered on size of drainage area. So we're looking for between 20 and 100 acres. And then they're placed in locations of highest flow accumulation along our field borders. Bioreactors are generally installed along the field border, so that's why that's happening. And when we think about bioreactors, for folks who might not be familiar with those practices, bioreactors are essentially large trenches or ditches that are installed in our agricultural landscapes. They're filled with wood chips, and then tile drainage water is passed through that bioreactor. During that water's residence time in the bioreactor, denitrification can occur with the wood chips serving as the carbon source, and then with water flowing through those anaerobic conditions. Potential sites are buffered by 100 meters, and then they're reviewed for their drainage capacity and their percent hydric soils, which must be less than 90%. So if we look at suitability for these bioreactors, we would like the surface area of the bioreactor to be equal or equal to or greater than the area required to treat the amount of upstream drainage at that location. And then the mean percent hydric soils within that polygon should be less than 90%. We want to basically avoid placing bioreactors in very poorly drained or our wetland soils. And so you can see bioreactor placement in these red squares. One thing to note is that the size of the squares are different, and those sizes reflect that upstream drainage. Here's an example of the output table that comes with the bioreactors. So you can see, for example, the flow accumulation in acres at the point of the bioreactor installation. So that's here in the BND_AC. The minimum acres, which is the minimum surface area of that bioreactor, and then the mean percent hydric soil of that area within 1 meter elevation of the installation point. Again, we would like that to be less than 90% to avoid siting these in areas with more wetland-like soils. The second, step 5, the second part of what I'm going to chat about today is impoundment siting. These are nutrient removal wetlands, wasp cobs, and our farm ponds. So we'll start with a discussion about nutrient removal wetlands. So we're looking for suitable locations for nutrient removal wetlands, which we identify along flow paths using some sort of threshold drainage, which we set. Essentially, there are points generated along that flow path, and at each one of those points, a wetland is simulated by creating an impoundment and then looking at water behind that impoundment. So the impoundment height as well as the buffer height. The primary practices that we're interested in with nutrient removal wetlands are CREP nutrient removal wetlands, which would be practices, conservation practices, standards 656 and 658. You can see in this table on the center part of the slide, the default and optional parameters for nutrient removal wetlands. I'll talk more about impoundment height and our spacing and impoundment height specifically. But the spacing, impoundment, and buffer height really, and suitability criteria really should be tailored to the geographic and landscape features that you're working in, and the standards that would be required for installing these nutrient removal wetlands, again, in the landscape that you would be working in. So when we think about the spacing, when I talk about spacing, I mean the distance in meters between each one of those sampling points. So for example, for an X spacing that we've selected, so for example, in this case, 100 meters, a point will be generated every 100 meters along a flow path, and then we'll test at each one of those points for suitability for those nutrient removal wetlands. The greater the spacing, the less time the tool will take to run, and the less points that will be considered as potential locations for a wetland. The smaller the spacing, the more points that will be considered and the longer that the tool will take to run. The second user-defined criteria is the height of the wetland impoundment in meters that will be simulated at each one of those sample points. Again, the default is 0.9 meters, but the user can change that height between 0.6 and 1.2 meters. And then finally, the last point of consideration would be the wetland buffer height in meters. On the right-hand side or the left-hand side of the slide, you can see examples from Iowa's CREP wetland standards, as well as constructed treatment wetland standards, and the variability in terms of wetland impoundment height and wetland buffer height. So understanding what the conservation practice standard is and using that standard to inform these different defaults is an important step in this process. So this is what the output looks like from nutrient removal wetlands. So you can see in the table that for each one of the wetlands and the buffer associated with that wetland, they have a site ID. For each one of the wetland buffer complexes, there's a contributing area in hectares. There's a pool area in hectares. You can see the buffered area versus that pooled area. You can also see the bank height, the bank elevation, the storage in acre feet, and then the variability storage in acre feet. So if we look at the image on the right-hand side of the slide, this green hatched area, that's the pool, that's the wetland. And then that blue hatched area is the buffer around the wetland. And this is the catchment or the drainage area that's associated with this wetland. One thing I again want to draw your attention to is to really think about reviewing these outputs with a critical lens. So you can see this wetland that's been generated alongside this road, and then the drainage area that's associated with that. So really thinking about whether that's an appropriately placed wetland or whether that would be excluded from the from opportunities is again an important consideration in the step. So don't just trust the tool, really think about the landscape that you're in and sort of what that output means in the context of the practice. So the next tool I want to talk about with respect to impoundments are WASCOBs, or water and sediment control basins. These are small embankments that are built perpendicular to a small watercourse, drainage way, or flow path in a particular agricultural field. So this tool identifies potential locations for those small embankments in watersheds from 2 to 50 acres in size. The user is going to provide the embankment height. So you're going to define the height of that WASCOB embankment as the measure from the bottom center of a drainage way or flow path. The default embankment you can see is 1.5 meters, but it can range from 1 to 4.5 meters. So again, really thinking about the slope of the landscape as well as the amount of pooling that you might want behind that embankment. So these embankments are generated as lines. You can see those polylines on the landscape in the image on the right-hand side of the slide. For each one of those polylines that are generated, there's a WASCOB ID that's given. You can see the potential contributing area in acres that would result from putting that embankment in. The embankment height, that's the default value. And then you can see other information associated with those embankments. The second part of this tool is identifying the ponding water that would back up behind that embankment. And so this tool is getting at the basin of the WASCOB. So it's delineating the area that would pond water up gradient of each one of those WASCOBs during times of high flow. So this process essentially involves burning each wascab into a filled DEM and then determining that ponding or sink region that's created upstream of each of those wascab embankments. And so the output from this process, you can see those wascab IDs. Those are associated with those same polylines that we saw in the previous step. And then you can see the storage in acre feet for each one of those wascab basins, as well as the surface area in hectares. So here's each one of those basins. You can see the straight line that's going to be associated with that embankment side, and then the ponding area behind that as well. So here's an image of those together. So you can see those wascab embankments. Those are those turquoise polylines. Then you can see that upstream area in that darker blue color. And there can be quite a bit of variability there. So you can have some relatively large wascab basins, and then some that are much smaller as well. The final impoundment I want to mention is farm ponds. So when we think about farm pond and farm pond locations, we want to identify areas where we can have we can achieve the largest storage volume with the least amount of earth fill. So good sites for farm ponds are generally ones where we can have a dam, an earthen dam that can be built across a relatively narrow section of a valley, have some steep side slopes that's going to permit that valley to be flooded. So when we think about some of the factors to consider here, we want to be careful about upstream and downstream side slopes of our settled embankments not being less than 5 horizontal to 1 vertical, or a 20% slope basically, or steeper than 2 horizontal to 1 vertical, a 50% slope. So this criterion specifies that the slope of that earthen impoundment, but here we also apply this criterion to the side slopes to avoid those locations that might either be too flat or too steep. The particular watershed that we looked at for the examples for this case don't have any farm ponds, so I don't have any to show you, but basically what you would identify are areas where that water would pool, and then drain and drainage areas associated with that as well. So the last step of the ACPF is riparian assessment. So in this step, we're going to identify riparian catchments and polygons, look at height above channel for those riparian areas, and then use that information to determine riparian function and the potential for saturated buffers, which are denitrifying practices. So the first step of the riparian assessment is to create riparian catchments. So the ACPF tool for this creates unique catchments along user designated lengths along each input stream reach corridor. So the only stream reaches that are considered here are our perennial stream reaches. So that's why it's really important in step 2 of the ACPF to make sure that you're identifying those perennial stream reaches, because those are the only reaches that are going to be considered for our riparian buffers. The riparian segment length for each one of these catchments can vary between 100 and 500 meters. So there's a 250 meter length value that is the default value for these, but that again can be adjusted by the user. The riparian catchment lengths are approximate lengths. Actual lengths would be determined by the number of riparian corridor elements that could be placed along a reach. So again, this is just identifying opportunities, and there's some variability here. There's also an adjustment that's performed as part of this tool to account for sinuosity, which can minimize some of the variability that we might expect. So when we look at catchments that are created along our stream networks, you can see those catchments in that image on the lower right-hand side of the screen. So each one of those black polygons, that's associated with a 250 meter stretch along that stream network. So each one of these catchments here is going to have one side adjacent to that stream network, and that side is going to be approximately 250 meters in length. You can see information about each one of those catchments, which can be really useful as you consider characteristics and conservation practice interests or need or potential. So for example, the proportion or the amount of cropped acres, the amount of pastured acres, and then the amount of tiled acres. So you can see that, for example, this particular catchment, 210-2, is going to have 28 cropped acres, and about 24 of those would be tile drained. So then we use those catchments to create our riparian attribute polygons, or RAPs. These RAPs are 15-meter polygons that are created for each one of those riparian catchments that we just created in our previous step. Each RAP is used as an opportunity to visualize the conditions that might be associated with each one of those riparian catchments. So for example, characteristics like slope, land use, and soil. The output riparian relationship class allows users to connect riparian catchments and these polygons to be able to visualize those features. So visualizing slope, land use, and soils. From the image in the lower right-hand side of the slide, you can see what those riparian polygons look like. Again, each one of these riparian polygons is associated with a catchment that we created in the last step. And each one is approximately 15 meters wide for this particular step. The next step is to evaluate the height above channel. So the height above channel uses some of the data and information that we generated earlier in the ACPF, including that unfilled DEM, the D8 flow direction grid, and the stream reach, the perennial stream network, to find the difference in elevation between each grid cell in that DEM and then that stream channel grid cell. So these elevation differences that we identify in this step are reclassified into height above channel categories, which are important because they estimate the potential for interaction between the riparian root zone and subsurface flows. And this height above channel step really impacts the functionality of these riparian polygons, which we'll talk about in the next step. So here's what that would look like in terms of a table and map. So you can see that the height above channel varies anywhere from basically less than 1 to 5, up to 5 meters. So the closer you are to that channel, oftentimes, you know, the variability is less. And then as you move out onto the landscape, there's an increase in that height above channel. And again, that's important because it helps us to understand how we can best design our riparian buffers. So this last bit here is about what we can do with those riparian polygons. So in the riparian assessment step, we can identify different functions for those polygons based on runoff delivery and the shallow water table width. So you can see that the runoff delivery and the shallow water table width are categorized into high, medium, and low. And then based on that matrix, there are different designs for our riparian buffers. So multi-species buffers, stiff stem grasses, deep-rooted vegetation, and then stream bank stability or stream bank stabilization. So when we think about assigning our buffer widths among those riparian functional classes or among those riparian assessment categories, we think about the width in accordance with the height above channel, as well as that relative runoff delivery ratio. So when we think about, let's start with our runoff delivery ratio in areas where we may see a relatively high runoff delivery, we may want to have a larger buffer size. So for example, 90 meters Those would be some of our largest riparian catchments where we might be seeing a relatively high amount of runoff delivery. As we move toward low runoff delivery, we can reduce the size of that buffer width in accordance to a reduction in the amount of overland flow or runoff that we might be receiving. If we look at height above channel, we can think about, again, changing the width of those buffers based on height above channel. So what that allows us to visualize is that, for example, in areas that we would identify as critical zone, we might have relatively large areas where we might be receiving a runoff from, and our width of height above channel may also be approximately 50 meters. So again, really thinking about these two factors as we assess riparian function is a critical step of this piece. So the purpose of this step, again, is to determine some site-specific opportunities for riparian buffer design. And we're going to look at drainage water as well as that riparian area. So each variable is linked to a high, medium, or low category, as I talked about before. And then we look at opportunities for those different riparian functions. So here's an output table from that step. So you can see the runoff rank has been provided here. And then that denitrification potential rank has been provided here. So thinking about that water table and the amount of denitrification that could potentially occur. Based on those factors, you can see different functions identified here, as well as the NRCS width and the buffer width as well. So for the riparian function assessment, you can join the polygon with the riparian function assessment table. There are lots of options for symbology here, so really pick and choose what you are interested in. And then again, similar with grass waterways and other tools, we want to be thoughtful about field verification. So here you can see that there's a polygon that has not been assigned a function, and it's sandwiched between two that have been indicated as multi-species buffers. You can also see that there appears to be forest cover here or tree cover. So really thinking about, is this already a buffer and what those opportunities might actually be? Again, an important step of field verification. The final opportunity are saturated buffers. So for each one of those riparian polygons, you can assess opportunity to place a saturated buffer there. Saturated buffers have some more specified needs than just other buffers. So there has to be a threshold of organic matter, so somewhere between 1.5 and 5.1%. We also want to think about coarse material that can exist near streams, and then thinking about those soil conditions in that particular riparian area. We also want to think about the maximum bank height, which can vary between 8 and 14 feet. So the user can set those thresholds. And again, I would encourage folks to look at the conservation practice standard if saturated buffers are available in the area that you're in. So for our particular example here, you can see these areas in red have been identified as potential sites for saturated buffers. And then you can see the table below, which identifies organic matter, coarse material, and then land use in each one of those catchments, which is an important consideration for saturated buffers. You can also see that for areas or for polygons where the saturated buffer is not suitable. So you can see, for example, here, there's also a reason why that saturated buffer is not suitable. So here, there's an indication that the saturated buffer would not be suitable because of some challenge with topography. So whether that's steepness in the area adjacent to the stream, or another factor that also provides a clue basically for why those might not be considered, and would be another important point to go out in that field and actually see if that site is not suitable, you know, or if there's something that might be done or amended to actually place that saturated buffer there. So with that, I think we have about a few minutes left. I know that's a lot of information. We basically stepped through the whole ACPF process here, but really wanted to give folks an opportunity to see the amount of data and really science that's considered to be able to identify these opportunities for conservation practice placement on the landscape. So I guess with that, I'll turn it back over to Marcel and Anne, and if there's any questions, I think both Josh and I would be happy to answer those.
Thank you, Emily, and thank you, Josh. That was great. Like you said, that what you just went through is what the other folks are covering in 5 weeks. So there was one question in the chat that Josh responded to, and it was, can you apply both constraints for the drainage water management, both the percent of field area and the minimum acreage? And Josh pointed out, you can't do that in the same tool run. You could run the tool twice, once for each method, and then compare the results. And I think that's a real important point for a lot of these tools, that you need to look at the results and then adjust and tweak, and it's a back and forth process. Emily or Josh, anything you wanted to add to that?
No, I think that is a good summary, Marcel.
As you're thinking of questions, I was taking notes, and here's some of the takeaways I took away from what you're talking about. And if anybody else wants to add in the chat, some of the things that what did you learn in the last hour and a half? We covered a lot of ground here. Throw that into the chat as well. We can add that here. These slides are in that folder that we shared at the beginning. I'll add that link again. What are people thinking right now? Just generally overwhelmed, or are you getting ideas for how you can use some of these tools? I think one of the important points here is that there's other ways besides running the ACPF that you can use those input layers, like the 6 years of cropping history is awesome, and the the field boundaries and so on. So there's other ways to use this, and like the riparian information that Emily was just showing, the denitrification potential and some of those things. There's a lot of neat information in the tables and in these various tools that you might have other uses for. So next week, on Tuesday, you'll be hearing some in-depth case examples. So Carl Gesch is going to talk about the Iowa watershed approach. Kevin Keener will talk about the Root River, and Joe Magner will talk about Beargrass Creek in Indiana. And each of these have used ACPF rather differently, either more with individual farmers or more with group meetings, or more for early in this planning stages versus bringing it in late in the planning stages. So I think we should have some good discussion. Oh, thank you, Adrian. Reminder for Illinois users, you have a kickoff at 11:15 this morning. So thank you, Emily. there are no questions at this point, let's wrap up. Oh, Judy, as someone who's used ACPF, oh, good to know there's some people there. There's no substitute for running the tools and getting some hands-on experience. Yep. And it's important for people who aren't the GIS user to be doing the field validating and working with the GIS person. There's just, you know, the online stuff only takes you so far. All right, have a good day, rest of your day, everybody, and we will see you on Tuesday. Don't hesitate to reach out if you have questions in between now and then.